Welcome, everyone, and thank you for joining us for today's Cloud Strategy Insider webinar, Resolving FinServ Data Challenges with AI-Powered Graph Technology on Google Cloud. My name is Meryl Lee, and I'm part of the digital events team here at Neo4j, and we're super excited to have you here with us. Today, I'll be joined by our guest from Google Cloud, Antoine Larmanjat, Technical Director, Office of the CTO, and Neo4j's Chief Scientist, Dr. Jim Weber. A quick note regarding questions before we get started. We invite you to submit any questions you have throughout the session using the Questions tab located at the top of your screen. We'll answer as many questions as possible at the end of today's presentation, and if we don't get to them all, someone on the Neo4j team will reach out to you directly, or you can send an email to webinar@neo4j.com and we'll get you pointed in the right direction. I also want to let you know that this webinar is being recorded. With that, I'll go ahead and hand it over to Jim to start today's session.
Thanks, Marilee. It's really exciting that Neo4j gets to present with Google, our partners in delivering Neo4j Aura to the cloud. And actually, Antoine, you're going to lead us off today, right? You're kind of in the driving seat.
Oh, that's a lot of that's going to be a hard task for me. Thanks a lot, Jim. Hello, everyone. So indeed, I'm Antoine Larmanjat. I work for the Office of the CTO. What we do at the Office of the CTO at Google Cloud is we spend approximately half of our time on Horizon 2 project and Horizon 2 solutions, working with products and engineering, and we spend the rest of our time talking to clients and customers and trying to understand what they need. One of the striking things that I was thinking about when we prepared this discussion, Jim and I, was like Google and Neo4j, we actually share one commonality. Both of our success is based on some form of graph. So it's PageRank for Google, it's really the foundation of our success, and for Neo4j, I mean, Neo4j is one of the leaders of graph databases. So this is something that we have in common. But Jim, maybe you can tell me a little bit more about Neo4j, the company, its licensing model, its technology.
Absolutely, be pleased to. So you're absolutely right. Google is the original graph company, right? So you have your founders there who are wondering about this graph of objects out there on the web, and they're doing these computations over the web to try to find relevant documents, and then the PageRank algorithm is born. Neo4j is kind of a little bit like that, but instead of assuming that the data will be out there on the web, we assume that the data's on disk. It's a database. So what we at Neo4j do is we build a graph database, and in fact, a platform of software around that database, where we can store graphs, the kind of networks, where we have nodes or vertices and edges or relationships that interconnect them. And our job is to make sure that you can store graphs safely and that you can query them performantly. And we call that technology a graph database. And it turns out that in Neo4j's case, Neo4j created the modern graph database born out of frustration, actually. It's quite a dark origin story for us. We have a group of people, my founding engineers over in Sweden, who are thinking about classifying photographs and other content. And they're finding that classifying content isn't a straightforward tree or isn't a straightforward hash map. It's actually a complex graph of terms that interact, particularly when you then throw in multiple languages and have concepts in different languages and so on. And it turns out the SQL they were writing, they were working with a relational database at the time, just got messy. SQL's amazing, love it. But it's a really awful thing for expressing path operations. So these folks went ahead and they said, well, what we really need is a path or graph API on top of our SQL engine. Terrible idea. You know why? Because it was successful. And what they did was they found the API was really nice for expressing these graph operations, but the underlying engine was being crushed by having to do so many joins. And so somebody bravely said, what we need is an engine that can do graphs natively. And then Neo4j was born. And Neo4j now, as a kind of modern graph database creator, I'm not, of course, ignoring the network databases from the olden days, but in the modern era, Neo4j created the graph database. And when we came to commercialize Neo4j, kind of 2007, 2008, beginning of our commercial journey, the NoSQL world had exploded, the open source world had exploded, and it was very obvious to us that the way that you get software into people's hands, into developers' hands, was to make it open source. Of course, this is a world remarkably that predates all of these phenomenal cloud offerings that now does much the same job. So we started off in this world where we'd make Neo4j open source. Over time, that changed a little. Cloud offerings came out, which makes it very easy to get software into developers' hands. We also changed our model a little, so we're now open core, where Neo4j is split between the core database engine, which is open source, and you can read that and tinker and actually learn how databases work. And some of our engineers actually came to us that way. And the stuff that enables you to run Neo4j 24/7 with fault tolerance and metrics and all of that, it ends up being closed source. And that's the kind of stuff that ultimately powers our cloud offering, like, for example, Neo4j Aura that runs on top of GCP.
Right. So as an ex-CIO in previous lives, I was a user of Neo4j. I can also personally testify how great it is. So Jim, you're the chief scientist of Neo4j. So what does it mean? Can you tell us a little bit more about your role there? What does a typical day look like in the wonderful world of Neo4j? What do you do on a daily basis?
I'd love to. So actually, when I first came to Neo4j, I ran engineering in the early days when we were a smaller engineering shop than we are today. Now that's run by someone far more competent. But I've managed to find an actually absolutely lovely role where I'm split between doing systems research, which is something I've been incredibly interested in since my days in academia, where I got the PhD moniker. And about half my time is spent with users and customers, actually understanding what they're doing with the technology, finding where they're succeeding, finding where they're bumping up against any rough edges, and helping filter that experience back at a technical level into our product and engineering teams. So it's rather a nice balance, because I get to look at the future. I follow the systems research and the database research community, but I'm very much grounded in the present experience of our users and customers by being with them as they deploy the technology. So yeah, best job in the world.
Great. Do you still get your hands a little bit dirty? Do you still have a look at code and stuff like this?
I do, in fact. So I know my engineering team will be cross if they discover that I'm trying to commit code to their code base now that I'm no longer an engineer. But actually, just this week, I had a large telecommunications customer, and one of my engineers who was with them asked some very fundamental questions. And I thought, I don't actually know off the top of my head how that is. One of the wonderful things about Neo4j being open source, it encourages everyone to read the source. So I did. I read the source, and I was able to say, look, in this code here, here's the authoritative answer to your question. So now and again, when people aren't scrutinizing me too closely, I still get into the source code.
All right. That must have been a humbling experience for your engineer. So let's dive a little bit into a topic of the day, financial institutions, and how we can help with technologies of Google Cloud and Neo4j financial companies. What we do see a lot especially with the financial institution is, in fact, the world is not that simple, and it cannot be represented in just tabular form, in just tables. And the tabular representation of information, with a fixed number of columns that never change, this kind of prevents the description of the world that's always changing, with changing characteristics and with emerging new features and so on. So relational databases are great if the world you describe does not really move fast, but it has kind of limitations when data structures are highly interlinked and not homogeneous. So instead, what is becoming more and more important is not so much how the data is stored, but how the data is linked to each other. And that's something that you've said at the beginning, but something that we see more and more. For example, we have many examples of this. Payments are a good example. The ability to analyze and visualize complex transaction relationships, the ability to detect anomalies in a payments flow that cannot be easily achieved with a traditional relational database. And the representation of company structures, for example, is also very important in risk management, in risk underwriting for the insurance world. So if you truly understand the complexity of a company structure, its relationships with its subsidiaries, the participations, the capital relationships, the relationship with other companies, then you can better understand and assess the risk you're taking. So overall, it's not so much about the data points themselves, but about the relationships between the data points, and you've mentioned that very clearly before. For fraud management and the detection of anomalies, it's especially important. And with the increased pressure of regulation, we see this all the time. So, Jim, now let's be a little concrete here. So can you show us what it looks like from a kind of a visual perspective with Neo4j?
Yeah, of course, I'd love to. So yeah, I'm completely with you there, Antoine. The number of use cases in finance that are connected data is astounding to me. I mean, when we first commercialized Neo4j, it was a really easy thing to get Neo4j into the telecoms business because they already understood network. So it was a really easy thing to say, oh, add social to your app for Neo4j. But what astounded and pleased me was as the financial industry picked up Neo4j, they were able to find a whole bunch of what are now obviously graph problems to me that weren't obviously graph problems at first, in compliance, in entitlements, in lineage and provenance and so on. And so let me show you what you can see here. I've just spun up just prior to us starting this little chat. This is an instance of Neo4j Aura running on GCP. And I have a database. Here we go, Neo4j GCP Aura demo. And I'm going to go ahead, I'm going to open it. Oops, I want to open it with Neo4j Bloom, which is our analyst-oriented visualization tool. So Chrome crashed my, let's restore that. So what do I have here? I have dots. I have actually loaded a demo data set into this database. It's not financials, it's actually a movie data set, but it's the same patterns that repeat in most domains. So here I've got movies and people. In finance, this will ultimately be, ultimate beneficiary and ultimate senders with all of the various, middlemen and so on that go on between it. So how do we represent a graph here? Well, you know what? I'm going to do a bit of vanity surfing. I'm going to type Emil Ephraim in here. Oh my word. Now, considering this is a movie database, it's a bit shocking to find Emil Ephraim, CEO of Neo4j in here. I can only suggest that my colleagues are pandering to my boss's ego. I do like, by the way, when other vendors take our data set with our movies in it. Emil ends up in other databases, demo data sets now, which is lovely. So look, I can type in Bloom like a Emil Ephraim, and we do a full text search, which is not very graphy. And we find that there's a record, a node here representing Emil. Well, okay, what else can we do? Well, it turns out, Antoine, not only did you inspire us in terms of graphs, but you inspired us in terms of Google search and this kind of sub-language called Googlish, where in the Google search bar, I can kind of type sort of fluent sentences and see where it leads me. So, okay, then, Emil Ephraim acted in, oh, that's nice, acted in movie. Oh, okay, so it's doing like Google style suggestions for me as an analyst. So now if I hit that, I'll run the query, and unsurprisingly, apparently, fake news of course, but my boss, who likes the name Neo, acted in the Matrix according to this this data set. So what we're doing here is we're kind of representing the underlying connected data records as nodes connected by directed and named relationships between other nodes. And you can see these nodes have label. The kind of beige nodes here are movies, and the green ones are persons. So let's do a bit more vanity surfing. I'm not quite so keen that Emil is the only Neo4j employee in here. Let's see if we've got a Jim. And we do. Oh, it's not me. Oh, that's disappointing. So we've got this, okay, famous actor, Jim Broadbent. That's as close as I can get to this data set. But now we can start to ask things. So I'll highlight those two nodes. And I can, for example, ask the tool to provide the shortest path. Oh, there we go. So now you can see, I'll just set this out a bit more nicely, that the shortest path between Jim Broadbent and Emil Ephraim is to go via the Cloud Atlas film, which one of the Wachowskis, Lily in this case, directed Cloud Atlas, and she directed The Matrix, and Emil apparently acted in The Matrix. And there's a really nice thing about graphs, that those kind of path operations are incredibly cheap. So we've got this kind of simple ping pong ball and wires metaphor, but using Bloom, anyone that can use Google can now start to explore graphs. You can engage with the graph.
Right. That sounds great. What we often hear is that, relational databases are inefficient when you have to deeply join many tables. And what large enterprises face on a daily basis is that these large tables that you need to join often come from various databases in heterogeneous environments. You have these large databases, they're quite heavy to migrate, and data can be represented in different formats. You have Mr. John Smith on the one hand that can be spelled something and then stored in many different ways, but still represent the same concept. And to understand, to link, to manage the complexity of this heterogeneity, we need different ways. So can you enlighten us a bit why these graph databases compared to how do they compare to relational databases, and why in some cases they are inherently more efficient?
Yeah, for sure. And I would say it is in some cases, right? Because there is no database that is universally the best at everything. Despite the hubris of some database folks, different engines are good for different data structures, right? So those of us that went and did computer science at university, we know that data structures have different good points and different bad points. And the challenge for us is to pick the right data structures to solve the right problem. Now, in Neo4j, what we observed when we were trying to emulate path operations in a relational database is that we ended up doing lots of joins. We ended up typically doing lots of recursive joins. And we know that the kind of a recursive join tends to work pretty well if the data set size is small or the number of joins is small, because the intermediate sets that you build tend also to be small enough that they'll stay in RAM. But as you start to do more and more joins, the intermediate sets that you build start to grow. And even then, for a modest database, at 4, 5, 6 joins, the size of an intermediate set could be large enough that it overwhelms RAM. Now, mechanically, this isn't the problem. Modern operating systems are brilliant. They say, okay, you're out of RAM. I've got this clever thing called virtual memory, and I'll make some area of disk, which is humongous, look like RAM. Awesome. Except now my query is chugging along at disk speed, which is so much slower than RAM speed. Even if you've got the latest, NVMe kind of disk, it's so much slower than the faster parts of your memory hierarchy. And so ultimately in a relational database, if you're trying to emulate a path query through joins, eventually you hit enough joins or a large enough data set size where you simply hit return and you don't know when your query is going to finish. And that's okay, right? Because that data structure is not great at doing graph operations or path operations. So we pick a different data structure. In Neo4j, the screen you can see in front of you, I'm going to lie to you slightly, and if you want the truth, you can always read the source code. But all this is a set of pointers. And if you remember from university, or in fact, I guess you're CTO at Google, you know this stuff intimately. But the one thing that modern computers are good at is the fetch execute cycle. So a von Neumann machine is really good at doing the fetch execute cycle. So grab some data from memory, bring it back into your CPU, process it, fetch again. Now, all Neo4j is doing in this case is grabbing a pointer from memory, dereferencing that pointer, looking where it goes, going to memory, fetching that pointer, and so on. And that fetch execute cycle, if you can get the data into the faster parts of your memory hierarchy, it's ridiculously fast. So being able to chase the pointers from Emil through the matrix and Lily Wachowski, Cloud Atlas to Jim Broadbent, that is a tiny fraction of a second to be able to resolve those pointers in this network. You're not building up a bunch of intermediate state along the way. You're just following the pointers. I think of it rather naively as I take a little robot, I drop it into a maze, and then the robot follows the maze of pointers until it hits the thing that I'm interested in and returns those records to me. So it's mechanically a lot more efficient, or it's a lot more mechanically sympathetic to how computers work than relational databases, which is why we get super high performance from it. We're just doing what computers are good at, and we're not doing what they're bad at.
Yeah, which is to link pointers, to fetch the data, to compute the data, and then to start again. So now I'm able to easily represent kind of a complex world of interaction with a graph database, but I need to query it. There's no kind of universal language on graph database like SQL for relational databases. Cypher is the main query language used to query Neo4j. Can you tell us a little bit more about it and show us what it looks like and what you can do with it and how it works?
Oh, yeah, that would be my pleasure. So look, what we just did there was, although we didn't know it, we wrote Cypher. We actually wrote some kind of Googlish, and under the covers, this was translated to Cypher. But actually, Cypher itself is really not hard to learn. So here's Neo4j Browser, different tool to Neo4j Bloom. It's intended for developers. And this particular user interface is connected to the same movie database that we saw earlier. So I'm just going to write a cheeky bit of Cypher here, return n. And what that says is, hey, database, find me a node. That's why we use the round parentheses, and return it. It's going to match patterns everywhere it can. So in this case, it's going to return every single part of the database. And there we go. This is a live. I realize that we're doing this live as we are on this webinar with a live instance of GCP somewhere in Belgium. And as we can see, look, I've got the graph. This is awesome.
Nothing is fake. I can assure the audience that nothing is fake.
So let me see. That's a good question. So if it's not fake, then I should also be able to find Emil, right? So let me find. So this time I'm writing match, but inside that first node, I'm saying that it must have the label person. Inside the node, it must have the key value pair name Emil Ephraim. And I'm going to say that it's connected via anonymous outgoing relationship, and I want to return it. So if I run that, there we go. So I have Emil Ephraim acted in the matrix here in Neo4j Browser. And if we recall back in Neo4j Bloom, the same records are appearing. So I don't think that's cryptographically secure as a proof, but hopefully it's informally good enough.
Yeah.
Now,
and look, we see that. So go ahead.
So now look, that is pretty easy. So, even if I know that you've used Cypher before in your previous life, if you haven't seen Cypher before, you can learn it in a morning. Right? It was designed specifically to be humane. It was designed by some very warm-hearted people, including a former SQL DBA who was so horrified at how complex SQL got that it was designed to be humane. So we can even start to do things now where we can say things like, okay, well, how do I find the shortest path between Emil and Jim? The same thing that we did with the Bloom tool, we can also write that in Cypher. So here in this top part, I'm saying, hey, database, find me a node labeled person where it has a property name value starting with Jim. So I'm looking for myself, vanity surfing here in the data. And then using this node or nodes that we find, give me the shortest path between Emil and Jim. At most, at path length 1 to 4, because I happen to know this data set, and path lengths more than 4 don't make any sense. Now, what's lovely about this 1.4 syntax that I'm highlighting, if you were a SQL DBA out there watching this, hi folks, I know you're out there, thanks for coming along. This is horrifying because you're all you're thinking, oh my goodness, like this could be a join bomb.
I'm already thinking of the nightmare of all the different joins you would have to do to achieve the same thing. Yeah,
exactly. But because we're only chasing pointers, this can be a quite cheap operation for us. And even in large graphs, this kind of thing has the property that the query latency is proportional to how many nodes or relationships you choose to query. It's not proportional to how big the data set size is.
Right.
So if I go ahead and run this now, well, here we go. There's Emil, who apparently acted in the matrix, and the matrix was directed by Lily Wachowski. Lily Wachowski also directed Cloud Atlas, and Jim Broadbent acted in Cloud Atlas. So now I've got this kind of technical view onto the database, which a developer would use, which is the companion view of the kind of Bloom-oriented Google-style view, which an analyst would use. So you've got both personas covered, your financial services developer, your financial analyst, who can use the data to, in their own convenient, comfortable ways, to gain value. And I draw, to the audience attention, things like the ICIJ, who produced things like the Panama Papers, with kind of, clever analysts studying the data, looking for financial incongruity, and indeed having developers building the software and underneath it, and building queries underneath it to help them solve these difficult problems. And that kind of duopoly or dual view tends to work very well.
And we see that the visual representation of the graph is also very, very important, contrary to in relational database, where it's more tabular and a bit different. So
the topology tells you so much, right? If you try to look at even this tiny graph here with an acted in, a directed, and so on, visualizing that as rows and tables takes a lot of ingenuity to figure out. But having the topology of the data displayed for you makes it really easy to consume. Yeah,
that's right. So if we go back a little bit to our financial customers that we interact with, what we see many examples of graph databases being used in many areas of financial services. Just to name a few, risk analysis is a typical use case, financial modeling, trading and risk systems, fraud management. We kind of alluded a little bit to fraud management a little earlier, anti-money laundering, with the detection of anomalies and stuff like this, detection of anomalies in payments that can be fraud, trade finance, and kind of buyer-seller relationships and how they interact with each other, company structures. I talked a little bit about this before. And outside of financial institution, you mentioned networking before, but there's plenty of areas where you have networks, like transport, routes, timetable management, with pricing and everything, and so forth. So is there a sector in particular, according to you, that you see growing and that is worth noticing from your perspective? Are there new use cases that we had not thought about before that are emerging?
Yeah, I think so I'm a victim of recency bias here, Antoine, but most of the folks I'm working with in finance right now are doing fraud detection, real-time fraud detection. And I think the reason that they pick up graphs is because the financial services community are always looking for the next best weapon in their ongoing battle against fraud. And anything that can give them that kind of half-second, 0.1 of a second advantage over the bad guys means that they win and the bad guys lose. And it turns out that what graphs give you for looking for fraud is the ability to process complex patterns of transactions and parties very quickly. So in the stream of transactions, you can say yes or no. And there's a huge bank based in the US that recently deployed a system using graphs. And in the first quarter of operations, they uncovered and saved several $1 million worth of fraud. There's also a large payments network that we work with, again, out of the US. It's peer-to-peer payments. And in that payment flow, phone to phone, they have to be able to say yes or no to stop money flowing between bank accounts and stop the fraudsters. And of course, they can't stop this, send it off for careful deliberation to a human or some batch processing engine. Customers are prepared to wait 24 hours now. It's like, I owe you 20 euros, Antoine, and you want it now. But of course, I don't want to be defrauded out of those 20 euros. So what the ability that GraphTech gives you, that Neo4j gives you, is the ability to scan hugely complicated patterns, spot the ones that you know are fraudulent, even in the background to be running unsupervised algorithms that start to surface more of these fraudulent patterns, bring those into your decision-making process seamlessly, all the time pouring streams of transactions through it and making these very rapid yes, no, yes, no, yes, no kind of decisions. I think that's hugely exciting because it's such a growth area.
Yeah, and what we see is that it's not only to protect themselves that these banks need to do this, it's also because there's an ever-increasing pressure from the regulators. The regulators want to make sure that all these fraud management systems are in with how they work. A bit about Google and graph databases in the cloud. We announced recently a large partnership with Neo4j. It's a deep relationship because it makes Neo4j a first-class experience where a customer can easily install a Neo4j instance from the Google Cloud console. Everything is taken care of. It's highly available. It's fully managed. It scales elastically in response to changing needs, and it has secured end-to-end encryption, and it's easy to use because it's also billed through GCP. So you get one bill, and it's quite easy. It's also very nicely integrated with our IAM, with our identity access management. So it's much easier for our joint customers to start with Neo4j on Google Cloud, unified billing, unified management, single console. And one of the most interesting features is that it runs on our leading containerization platform, GKE. So what was the rationale behind using GKE for Neo4j? What did you like about it?
So building a good database as a service is hard, right? I mean, you folks at Google have like a million geniuses to throw at this, and it's still hard. And we have far fewer than a million geniuses to throw at it. So our thinking here was, how do we make sure that our technology can gain purchase on the cloud platform as easily as possible? And it turns out that GKE was the right thing to do there. We had some folks on our team who are very familiar with Kubernetes. We worked in partnership with the Google Kubernetes engineers to make sure that our platform was just in a kind of frictionless way being able to deploy onto GKE. And for us, what it meant was we didn't have to worry about some difficult problems, right? We could give ourselves a boost by letting a GKE do a lot of that heavy lifting, right? We could interact with, once we'd kind of built our own infrastructure to map onto it, we could declare the capabilities we wanted from GKE. So that's why we wanted to run on it. Now, look, Google's obviously the king of Kubernetes. So our experience was made a lot simpler by Google providing that platform and allowing us to focus on the customer journey, right? Allowing us to figure out how Neo4j runs with respect to the infrastructure Google provides and how to make the customer journey onto Neo4j Aura kind of, again, frictionless and, dare I say, even pleasurable, without having to worry about the kind of down in the details cloud infrastructure. Now, partnering with the Google Cloud engineers on this was amazing, right? So the Google Cloud engineers came and they gave our infrastructure a real good kicking, and we came out of it cleanly, which was a proud moment. I have to say I'm very proud of my engineering team for that. But what it meant was that when we deployed onto Google Cloud, it was a flawless experience, and people were up and running with it really quickly. I would like to say one thing which I thought was even cooler than that. One of my senior engineers, just said to me, like, GCP is like science fiction. They tell us that they've moved workloads for us, and we disagree with them, and then we check the logs, and they were right. So things happen in terms of continuous provision of service on GCP, which is so responsive, which keeps our database service running so well, that it's the closest thing that we've seen to science fiction. And end users just get this seamless continuity of service because GCP is so good at managing the underlying infrastructure for us. It's quite astounding.
Thanks. That sounds great. So we do see a great momentum with customers on both Google Cloud and Neo4j. But as the chief scientist, I guess you have different horizons. So you must be working on improving the current system, but also thinking about the next steps. from a technology perspective. So are there any trends that you would like to share with us that you think will emerge in the future of graph databases and for Neo4j in particular? Don't disclose anything too secret, but if we could have a sneak peek into what you're doing on your free time, that would be great.
Free time? Oh,
Free time? No, I shouldn't say that.
Sunday evenings. Yeah, I think the big trend, the mega trend, if you like, that's graphs. I noticed that you folks are definitely on the kind of graph mega trend. There was recently quite a good article that some of my folks and some other kind of luminaries in the industry published about the future being big graphs, and I fully buy into that. I think that graphs are going to come to dominate data, as in database. They're going to come to dominate analytics. They're going to come to dominate machine learning in the coming decade. And that doesn't mean graph database everywhere, of course. Google is a fine exemplar of graph processing being an incredible way to build a business, but I think graphs are the mega trend. Now, for me, with kind of chief science hat on, I think there are like a number of really interesting research challenges to be solved here, so that we can use graphs, conveniently at peta or even exascale. And these are obvious things for a database person, things like query planning and transaction protocols and so on, that will need to grow so that we can query and store these huge volumes of connected data conveniently and safely. But I think there's also something coming along around exotic hardware, and that's a trend that started to creep back on us. For the longest time, hardware was boring, right? And no disrespect to the hardware folks, this is my own stupid opinion at the time, where all hardware was a beige box. And then at some point, all hardware was a virtual machine on a cloud provider, and it was kind of lowest common denominator.
Right.
And the hardware folks are amazing, right? They're such bright people. And in the background, they've been making hardware really, really cool. So for me, I've got my eye on... Sorry, go on.
No, sorry. Do you think so at some point there will be like graph database accelerators from a hardware perspective?
I think so. We already see the beginnings of that, Antoine. So we're seeing people looking at, say, GPU as a kind of first step towards that, or even things like FPGAs. Can I program a chipset to do a complex graph operation? And indeed, now FPGAs are starting to appear on disks. So isn't it nice that my query planner could actually say, hey, I'm going to push this query down to the disk and have it done on the SSD, which would be kind of amazing. We also see now people building novel silicon. Not at all volume players, kind of specialist niche players, but building novel silicon to deal with graph problems. And I think in the course of the next decade or so, as graph really finds its purchase, it would not surprise me at all if Google Cloud starts offering some of these kind of what are today niche technologies for widespread use.
These topics are definitely topics that are of great interest to us, indeed. So Google is largely an AI company. Today, we see AI playing an ever-increasing role everywhere. The representation of a neural network, it looks a lot like a graph. I guess you must be thinking a lot about AI. What are your areas of interest there? Can you tell us a bit about how you approach this?
Yeah, for sure. So, again, we are fast followers of you folks. So we look at what you do, what the folks at Edinburgh University are doing, what the folks at MIT are doing, and it's clear that you're leading the pack. And the message coming out from that kind of, Google, Edinburgh, MIT kind of crowd is that graphs are the future. There was a joint position paper, in fact, very influential position paper that you folks published, where you set out the case for graphs being the fundamental basis for transfer learning, and therefore a human-like AI that can really start to learn. Now, today we're not there, right? That's clearly our lighthouse. That's our research goal that we're heading towards. But graph machine learning is incredibly popular today, whereby we can take graph features like PageRank, the PageRank of a node, or centrality of a node, or so on, and we can use those features alongside other traditional features, age or postcode or what have you, as features that we can ship into a machine learning pipeline. Because of course the machine learning folks, as you're saying, if I only had more features, I could give you a better model. Well, a graph has more features. It has neighborhood, it has locality, it has centrality, it has PageRank, it has all of these kind of things that you can harvest easily, and you can use them to build better models. Or you can even now, using node embedding algorithms, you can encode the topology of the graph into your machine learning model. So using random walks or fast random projection or what have you, you can take the graph of interest and encode that into your machine learning model so that you can get an even better outcome or even better prediction from those models. Now, that's where we are today. But in the future, I think it's very clear that we're going to be following the kind of AI leaders like Google. And as those discoveries are made, we're going to be figuring out which parts of that are, hyperscale computation that are only accessible to Google, and which parts of that kind of emergent AI world that we can bring into the Neo4j graph platform, which we can then make consumable for people who are today's Neo4j users and tomorrow's.
Great. Wow, that's super interesting. We have work on our plate until the end of time. That's great. I think that's been really, really, really entertaining and interesting and rich what you just shared with me and with us. I think Google Cloud is always very excited in partnering up with Neo4j. We do see a lot of potential for graph databases and graph in general. We are super motivated to making it a seamless, super easy experience for our customers. So it's been a great discussion. I was wondering if we had questions from the audience, and if not, we will say thank you.
Hi, Antoine. Hi, Jim. This is Marilee. What a great conversation. And I just love that Emil is featured as appearing in the Matrix. That's classic. I love that. But we have had some questions from the audience. So let's get started with those. Here is one that asks, is it easy to move from Neo4j on-prem to Neo4j GCP?
Yeah, I'll take that. So the Neo4j Aura team have a toolkit to help you push your data onto Neo4j Aura on GCP. Hop on over to the Neo4j Aura site, get connected with us on the forums, and we can help you make that move onto Aura.
Great. Thank you so much. And here's another one. Let's see. What are the most common Google Cloud services used, and are there any special considerations needed to deploy them?
Well, we have lots of popular services and solutions on GCP. I think that we see great momentum with everything that's related to containerization, so GKE, Kubernetes, and services like this. And we see also great momentum on BigQuery and the ability to use BigQuery in an AI context, with the ability to create models with very little to no ML experience directly on BigQuery, with things like AutoML and things like this. We do see a lot of potential there.
Great. Thank you so much, Antoine. And this has come in a variety of different ways, so I'm just going to sum it up. But basically, what's the best way to get started?
Well, I mean, I got started in a couple of minutes there with my little database running on GCP. It took a couple of clicks and I was up and running in a free version of Neo4j. But really, when you're building a real system, you're not going to be just clicking on that. The easiest way if you're building a real system is to get Neo4j Professional, Neo4j Aura Professional on GCP, which you can get through the GCP marketplace. And if you've got something that you want a bigger system, you've got some graph dirt under your fingernails and you're trying to produce something bigger, or you've got multiple departments, or indeed your whole business that wants to have access to Neo4j Aura, you can also talk to Neo4j and Google about Neo4j Enterprise Aura on GCP for those real big demanding systems.
Great. Thanks so much, Jim. And it looks like we're just about at time. So I want to remind the audience that if your question wasn't answered, someone from Neo4j will reach out to you directly, or you can always send me an email at webinar@neo4j.com, and I'll be sure to get you pointed in the right direction. Jim, Antoine, thank you so much for your time today. It was such a great conversation. Really enjoyed it. And for
Thank you. Thanks, Antoine.
Oh, sorry.
Thanks a lot. Thanks, Jim.
And for those in the audience, thanks for joining us. And I'm going to wish you all a great day. Thanks so much.